Hello friends, welcome back to another exciting video of physics and animation. In our previous videos, we have explored the fundamental concept of electric charges, their properties, and the nature of the forces exerted by them. Today, we are going to dive deeper and uncover the answer to a crucial question: how much force do charges exert on each other? As we all know, mass is a characteristic property of any particle or matter, which leads to the force of gravity between bodies. Newton formulated the law of gravitation, which states that the force of gravity is directly proportional to the product of masses and inversely proportional to the square of the distance between them. Combining these equations and removing the proportionality sign gives us the universal constant of gravitation. Similarly, electric charges also exhibit a characteristic property that leads to the force of attraction or repulsion between them. The famous Coulomb's law, formulated by the French physicist Augustin de Coulomb after extensive experimentation, states that the force between 2-point charges is inversely proportional to the square of the distance between them and directly proportional to the product of their magnitudes, and the force will act along the line joining the two charges. Please note that when the linear size of a charged bodies are much smaller than the distance separating them, the side may be ignored and the charged bodies are treated as point charges. When we combine both equations and remove the proportionality sign, we get a constant c, and the equation for the force between two charges, which is F equals c times q1 q2 divided by r square, where r is the distance between the charges and c depends on the medium between the charges. This constant is equal to 1 by 4 pi epsilon m, where epsilon m is the permittivity of the medium between the charges. Permittivity is a property of the medium that affects Coulomb's force. The higher the permittivity of the medium, the lower the effect of the force between the charges. But you can ask a question about why the role of 1 upon 4 pi is important here. Let's try to understand this. Suppose we have charge q1, whose effect, if seen in a 2D environment, would be in circular area. When we talk about a circle, the angle subtended at the center of the circle by an arc is equal to the arc divided by the radius. If we consider the arc be the complete circumference of the circle, which is 2 pi r, then we will get an angle of 2 pi radians, which is a plane angle. We can say that the charge is creating an electric field lines around itself in 2 pi radians. However, in reality, the impact of the charge is in a 3D environment, and it appears to be spherical. Just as we use the term plane angle in 2D space, in 3D space we use the term solid angle. Mathematically, for a sphere, the solid angle is equal to surface area of the sphere divided by the square of the radius, where the surface area of the sphere is 4 pi r square. Simplifying the equation, we get 4 pi as the value of the solid angle for a sphere. Therefore, we can say that the impact of the electric field lines of a charge in 3D space is spread over a solid angle of 4 pi. However, if we look closely, a point charge q1 can only affect another point charge q2 through the one possible electric field line out of the 4 pi possible field lines. This is why we use 1 upon 4 pi in the formula of electrostatic force. So we just learned that the permittivity of a medium affects the ability of a charge to exert force on another charge. But if we talk about the best medium for transmitting force, it would be a vacuum, which we also called free space. We represent the permittivity of free space with epsilon naught, which has a value of approximately 8.85 into 10 to the power minus 12. This value is almost the same for air as well. Other materials such as glass, water, and PVC have different permittivity values. Such a complex values can be a bit difficult to remember. So we use relative permittivity epsilon r instead. Relative permittivity of a medium is equal to the permittivity of a medium divided by the permittivity of free space. Since the permittivity of free space is lowest possible value, the permittivity of any medium can never be lower than epsilon naught. Therefore, we can say that the relative permittivity will always be greater than 1. The physical meaning of relative permittivity is simply how much times greater the permittivity of a medium is compared to the permittivity of free space. For example, generally, glass has relative permittivity of around 4, water has relative permittivity of 81, and PVC has relative permittivity of 3. We can use the formula of relative permittivity to express the permittivity of a medium epsilon r times epsilon naught. Now let's replace the permittivity of a medium epsilon m in the formula for Coulomb force with epsilon r into epsilon naught. We know that 1 upon 4 pi epsilon naught is a constant value which is approximately equal to 9 into 10 to the power 9. We now have a modified equation for Coulomb's force in the terms of relative permittivity epsilon r. Now let's find the SI unit of permittivity. When we modify the formula for force, the formula of permittivity can be written like this. We know that the unit of charge is Coulomb, the unit of force is Newton, and the unit of distance r is meter. By simplifying this, we get the unit of permittivity as Coulomb square per Newton meter square, which also can be written as Coulomb square Newton inverse meter minus 2. So that's all for this video. Thank you so much for watching.